Okay, Dr. B here, and let's talk about haloalkanes. They also go by the name alkyl halides. Their general formula is very close to an alkane, but instead of being 2n plus 2, they're 2n plus 1, since the X, being the halogen, fluorine, chlorine, bromine, or iodine, has substituted for the hydrogen of the alkane from which they might be derived. They are electrophilic at the carbon that contains the halogen. Take a moment and make sure you're comfortable with that. That means that if you have an Rx, where R is some sort of hydrocarbon, that carbon right there will be electropositive. Why? Because the X is electronegative. It has a greater desire for electrons, so it'll be partially negative there and partially positive there. That means that that R group is what they say as subject to nucleophilic attack. Something electron-rich will attack that carbon and spit out the halogen. So that's what it is, prone to nucleophilic substitution. In this case, we're only going to consider the reaction with a hydroxide. It'll attack that carbon and kick out the chloride. But we're going to take a look at this in quite a bit of detail, since there's two different primary mechanisms going on depending on the nature of the alkyl halide. If it is primary, meaning only mono-substituted, then it cannot form any kind of stable intermediate. That hydroxide will attack that carbon, kick out the chloride. At some point it will be half reactant, half product. We call that the transition state. Dots means the bonds that are being made, and the bonds that are being broken is also by dots here. That carbon-chlorine bond is being broken. This whole thing has a negative charge, but it's well dispersed, and then finally you end up with your alcohol. Can you see that there's an inversion going on? It's coming in from this side and then throwing those things over there so that the stereocenter is inverted. I hope you can see that. This will invert the stereocenter, so it'll change it from one enantiomer to the other. That can be important for catalysts, digestion, things like that. If you want to make the reaction go faster, use what they call a polar aprotic solvent. That means it's polarized, but it doesn't form a hydrogen bond. It's actually a surprisingly rare list. Things like dimethyl sulfoxide, dimethylformamide, and a few others are polar aprotic solvents. You don't want to have something that could form a hydrogen bond that could slow things down, and you want to let this relatively uncharged intermediate just do its thing. So it can polarize the intermediate. That's nice, help break bonds, but you don't want to have it to form a powerful hydrogen bond. So polar aprotic solvents can make it go up to 1,000,000 times faster. If it's not a primary alkyl halide, but a tertiary alkyl halide, the big deal going on there is that each of these alkyl groups are weakly donating in an inductive sense. That means their natural desire is to donate electrons just a little bit. Therefore, things won't just happen all at once, because they can stop once that halogen leaves and form what they call a carbocation. In this case, this is a tertiary carbocation. That's a pretty stable gizmo because it's inductively donating at each of those alkyl groups. So this will like form this and stick around for a second. Way less than a second, but you get the idea. RLS means rate limiting step, and so the rate only will depend on the slow step. If you've got a slow thing and a fast thing, you cannot go faster than the slow thing, and therefore that's called the rate limiting step. The concentration of that haloalkane right there is the only thing that really affects the rate of the reaction in terms of concentration. Steric hindrance can be a problem. This carbocation stability can slow things down a little bit. But interestingly, it's important to note that SN1 reactions, nucleophilic substitution type 1, are generally faster than the SN2, nucleophilic substitution bimolecular, where everything's happening at once. 1 means, I suppose, that you're forming this carbocation fine. The polar protic solvents help in this case because it's good to stabilize that carbocation. So something that can hydrogen bond, methanol or ethanol or something like that, can be a good solvent for this reaction. As always, you have to make sure your solvent doesn't turn into a reactant, so you have to be careful there. And if you're trying to maintain a stereocenter, where you're in big trouble here, because this is a planar thing, and the hydroxide or the water molecule that contains the OH can attack from either the top or from underneath here. So you're going to lose your stereochemistry at this point. You'll get a racemic mixture. And that's typically bad news for scientists who need to maintain a chiral center. So in the purest sense, this can give rise to two substances. They'd be enantiomers. And by the way, this has to lose its final H plus for the reaction to continue. So if it's with water, the presence of an acid would help, and it would be catalytic. If you have secondary alkyl halides, well, we're just not going to go there because there'll be a little bit of each, mixture of SN2 and SN1. Some general notes is that in terms of the reactivity of two competing things going on, if you have a small leaving group, that'll make it faster. So in that respect, the fluoride would be much faster than an iodide. On the other hand, the bond strength is also weakest for the big halogens. So that dominates, and that means the iodides react fastest, fluorides slowest. That's the take-home message, but you might be asked to give a competing factors type argument, and there it is right there. If they show you an energy profile, since this is a two-step process and that's a one-step process, the SN1 is very easy to recognize because it's a two-headed monster, right? You have the transition state here, and if this is time, I think this would be the slow part. So I have a long length there. This would be the fast part, so I have a very fast, small amount of time for that one. And so you have two intermediates, and then you have your product, whereas this is all just a bimolecular, they call it, which is kind of confusing. That means everything's happening at once. You only have one transition state here. Okay, that's, I believe, all we have. So the only reactions that the haloalkanes undergo, really, at least the only ones we'll be considering, and that's certainly the case. There's lots of other reactions here. But the only one we're going to consider is the reaction with hydroxides to convert an alkyl halide into an alcohol. This is an introduction to haloalkanes.